Today, we are wrestling with a really fundamental truth about data that evolves over time. What happens when one data point is influenced by the one right before it? Your standard statistical tools, well, they can become dangerously unreliable.
They certainly can.
We're tackling that critical challenge.
Yeah.
How do you actually run a regression when your data points are, in essence, talking to each other?
Right. And that conversation between data points, that's the technical hurdle we call autocorrelation or serial dependence. It's central to time series.
Right.
You see, for time series analysis, we have this absolute bedrock assumption. The errors, the leftovers, after your model has done its best predictive work, they must be statistically independent.
That's the white noise requirement, isn't it?
Exactly. If those residuals, the errors, are correlated over time, it means your model is fundamentally missing some predictable pattern.
And ignoring that.
If you ignore that statistical hangover, your model parameters might look precise, the standard errors seem small, but your inferences, your conclusions, they're likely just plain wrong. You end up with spurious results.
Okay, so the mission today is to equip you with the, let's say, the heavy-duty theoretical toolkit you need to get sound inferences when you've got these correlated errors. We're definitely going beyond standard ordinary least squares here. We'll be digging into some powerful diagnostic tools, looking at complex model transformation techniques, and even sophisticated predictability tests.
All designed to make our temporal models trustworthy, robust, and actually useful.
So where do we start?
We have to begin with the foundation, understanding the cross-correlation function, the CCF. Now, this isn't just your basic correlation between two variables, say height and weight. It measures the relationship between two time series, let's call them X and Y, but specifically when one is offset in time.
The lag.
That crucial concept, yes, the lag.
And this is how we start identifying those potentially vital leading indicators, right?
Exactly. Think about nutrient runoff into a lake that's series X and maybe the resulting algal bloom is series Y.
Right, the bloom doesn't happen instantly.
Precisely. The peak bloom won't likely occur the very same week as the highest runoff. The CCF is the tool that tells us, with statistical rigor, if that link exists and whether the bloom typically follows the runoff by, say, 2 weeks or maybe 6 weeks. It quantifies that delay.
But I sense a but coming.
There is a big one. We immediately run into a significant risk. Spurious cross-correlation. This is a really crucial diagnostic step to get right.
Okay, explain that. Spurious correlation.
Imagine if both the nutrient input and the algal bloom are individually highly autocorrelated, meaning high values tend to follow high values in both series just on their own.
Independently.
Yes, independently. They could then appear correlated with each other at some random lag just by sheer coincidence of timing, even if there's absolutely no true underlying predictive relationship between them. So that sounds like a major statistical trap. You could end up building a whole complex model based on what's essentially an accidental alignment because both series just happen to trend similarly over time.
That's the danger. So how do we filter out that internal noise, that self-correlation? That's where specialized methods, like certain bootstrapping techniques, come in.
How does bootstrapping help there?
Well, standard methods for calculating confidence intervals around the cross-correlation assume independence, which we know is violated because of the autocorrelation within each series.
Right.
So specialized bootstrap methods work differently. They estimate a much more honest confidence interval by simulating the data after specifically accounting for that internal stationary autocorrelation structure already present in each input series.
So it adjusts the goalposts for what counts as a real correlation.
In a sense, yes. It filters out the noise introduced by the individual series' own memory, giving us a cleaner picture of whether X actually predicts Y, beyond what you'd expect from random chance given their internal dynamics. Okay, so CCF is our first diagnostic pass. It tells us if a lagged link might exist, and maybe even something about its nature. Linear versus just monotonic.
Correct.
Yeah.
We can use Pearson correlation within the CCF framework to check for linear relationships, or Spearman for more general monotonic ones. It's vital exploration before committing to a full regression model.
All right, so let's say the CCF suggests a relationship at a specific lag. We move to building the model. But if our first attempt, maybe a simple OLS regression, shows those residuals are still serially correlated.
Like if the error from yesterday seems to predict the error today, perhaps following an AR1 process, an autoregressive process of order 1,
then we know standard OLS assumptions are broken. our estimates are compromised.
Irrevocably broken. And this is where the core theoretical method of model transformation becomes essential.
Model transformation sounds complex.
Think of it as a kind of statistical sleight of hand designed to make the assumptions hold true again. We start with our original regression model, where the errors, let's call them epsilon, are correlated. The trick is to mathematically rewrite the entire model. We essentially pull the autocorrelation parameter, say, the phi coefficient for that AR1 error process, out of the error term and incorporate it directly into the regression structure itself. This effectively transforms the original variables.
So we take the predictable pattern we found in the errors and force it into the prediction part of the equation.
Precisely. You're building the error structure into the model structure.
And the payoff.
The mathematical payoff is huge. The transformed equation yields a new set of residuals that are hopefully perfectly well-behaved white noise.
So they satisfy the OLS assumption. We've restored statistical integrity.
Exactly.
But wait, if we're pulling a parameter like phi out of the error term and mixing it in with the original predictors and the response variable, what's the catch? Can we still just use simple OLS on this transformed model?
And that is the crucial trade-off. The resulting transformed model is generally no longer linear in all its parameters.
Not linear. How so?
Well, for example, the constant term, the intercept, in the transformed model often becomes a complex product of the original intercept and that autocorrelation parameter, phi.
I see.
We've basically turned a simple linear setup into something more like a statistical Rubik's Cube, where solving for one parameter instantly affects the others in a nonlinear way.
Okay, so if the model is now nonlinear in its parameters, that means ordinary least squares is out the window. OLS relies on solving simple linear equations.
That's absolutely right. OLS just can't handle this kind of nonlinearity in the parameters.
So what do we use instead?
We have to move to more sophisticated estimation techniques. Typically, this means using maximum likelihood estimation, or ML.
Maximum likelihood.
Yes. It's computationally more intensive. It essentially uses iterative optimization algorithms to search for the set of parameters, both the regression coefficients and those autocorrelation parameters, that maximize the probability, the likelihood of observing the actual historical data we have.
And it can handle the nonlinear parameter relationships introduced by the transformation.
Correct. It's designed for exactly these kinds of situations.
Now, within this framework of handling correlated errors, you mentioned there are sort of two main philosophies or structures for how the external predictors, like our nutrient input, interact with the response, the algal bloom.
That's right. Two general approaches. The first, and often preferred method if interpretability is key, is called regression with RMA errors.
RMA errors.
In this structure, the predictors, the X variables, are modeled as directly influencing the response, Y. The RMA structure, that autoregressive moving average component, is confined only to cleaning up the error term, the residuals.
Why is that preferred?
Because the coefficient for your predictor, X, retains its simple direct interpretation. It represents the marginal effect of X on Y, holding other things constant without being complicated by the model's own dynamics.
Okay, that makes sense for clear interpretation. What's the second approach?
The second approach is often termed Aramax. The X stands for exogenous inputs.
Aramax. How does that differ?
Aramax feels inherently more complex because it explicitly includes lagged values of the response variable itself past values of Y, right alongside the external regressors, X, in the main prediction equation.
So Y is predicting itself, plus X is predicting Y.
Exactly. And here's the critical distinction. In an Aramax model, the coefficients on those external regressors, the X variables, they lose their simple direct interpretation.
How so?
They must now be interpreted conditionally. The effect of X on Y is now estimated given the influence of the past values of Y that are also in the model. By forcing Y to predict itself, you often diminish the apparent independent role of your external predictor, X.
Right. It muddies the waters on the direct impact of X.
It can, yes. Choosing between regression with RMA errors and Aramax depends heavily on the specific goals of your analysis.
Okay, that covers a lot of ground for linear models, even transformed ones.
Yeah.
But as we know, real-world time series data rarely follows that neat, normally distributed path we often assume.
Absolutely. We need to shift gears significantly here.
What happens if our data is, say, highly skewed? Or it's discrete, like count data. Imagine tracking the weekly number of insurance claims after major storms. Lots of zeros, perhaps, then some big numbers.
You've just hit the wall of normality. Count data, like insurance claims, often exhibits features like heavy tails, maybe excess zeros, and very commonly, Over-dispersion,
Over-dispersion.
where the variance of the data is much larger than its mean. This completely violates the assumptions of standard linear regression and even the transformed ARMA models we just discussed, because they typically rely, at least implicitly, on the residuals being normally distributed.
So standard fixes for autocorrelation aren't enough if the fundamental distribution of the variable is wrong.
Precisely. This requires a different approach, a paradigm shift even. We move from just fixing the error structure to modeling the entire distribution of the response variable more flexibly.
And this brings us to GAMLS.
Exactly. Generalized additive models for location, scale, and shape.
Generalized additive models for location, scale, and shape. Write that down.
GAMLS offers tremendous flexibility. It extends the idea of generalized additive models, or GAMs, by recognizing that the mean, or the location, isn't the only aspect of a distribution worth modeling.
Okay.
GAMLS allows you to model not just the location, like the average number of claims, but also the scale parameter, which relates to variability or volatility, and even shape parameters like skewness or kurtosis of the response variable's distribution.
And you can model these using predictors.
Yes, using external predictors, potentially with smooth, nonlinear relationships captured by additive functions. So you might model how the average number of claims changes, but also how the volatility of claims changes, maybe depending on the storm intensity or time of year.
So the real insight with GAMLS isn't just picking a better distribution like using a negative binomial distribution for those over-dispersed claim counts instead of assuming normality.
That's part of it. Choosing an appropriate distribution is key.
But the bigger idea is realizing that the volatility, the scale, or even the shape, the asymmetry, might also be time-dependent and predictable themselves.
Exactly right. It forces us to think beyond just modeling the mean. We can explicitly model why claim volatility might change over time, perhaps using non-parametric smooth functions to capture complex nonlinear patterns without forcing them into rigid shapes.
That sounds incredibly powerful.
Yeah.
But how does it handle the original problem, the autocorrelation, the time dependence?
That's a specific methodological point with GAMLS. Unlike some time series specific packages, standard GAMLS implementations don't usually have a built-in function to just specify use an ARMA error structure.
So we have to address the autocorrelation manually.
Correct. The common approach is to mimic the structure of an autoregressive model by explicitly including lagged versions of the response variable itself as predictors within the GAMLS model equations.
So we're back to including YT1, YT2, etc. as predictors, similar in spirit to AirMax.
Similar in spirit, yes. We essentially build the AR part of the model directly into the predictor set for the location, or potentially even for the scale or shape parameters.
What's the trade-off there?
We likely sacrifice that theoretically pure white noise residual structure that the explicit ARMA error transformation aimed for. But what we gain is the monumental ability to handle the full distributional complexity of highly non-normal time series data, which might be far more important in many real-world cases.
Okay, so we've covered identifying relationships with CCF, building complex linear models with transformations, and handling non-normal data with GAMWAL-S. Let's pivot one last time, from modeling relationships to rigorously testing influence.
Right. This takes us to the concept of Granger causality.
Granger causality. Now, this is purely about prediction, isn't it? It's quite distinct from proving physical causality like you would with a controlled experiment.
Entirely distinct. Granger causality is defined by a very straightforward predictive test. We say time series X is Granger causal to time series Y if.
If what?
If, by adding the current and past values of X to your prediction model for Y, you significantly reduce the forecast error variance for Y's future values compared to a model that only uses past values of Y.
So it's fundamentally asking, does X provide statistically significant new predictive information about Y that the history with Y alone didn't already capture?
That's the essence of it. Does knowing X help you predict Y better?
And this framework can uncover complex dynamics too, right? Like instantaneous effects or feedback loops.
Yes. We can test for instantaneous causality. Does the current value of X help predict the current or very next value of Y, even beyond all past information? And if we find that X Granger causes Y and Y also Granger causes X, then we identify that cyclical relationship we call feedback.
How is the test usually performed?
Typically, it's done using a statistical test like the F-test. You compare two nested regression models.
Nested meaning one is a simpler version of the other.
Exactly. The simpler restricted model predicts Y using only its own past values and maybe other control variables. The more complex unrestricted model adds the lagged values of X as predictors.
And if the complex model is significantly better.
If the F-test shows that adding the lags of X results in a statistically significant improvement in prediction, a reduction in error variance, then we reject the null hypothesis of no Granger causality and conclude that X does Granger cause Y.
But you mentioned earlier there are pitfalls here too, especially with trending data.
Oh, absolutely. The biggest technical prerequisite is stationarity.
Meaning the series' statistical properties like mean and variance don't change over time.
Correct. If both series X and Y are non-stationary, perhaps they both just have strong upward trends over time, they will almost always appear to be spuriously causal, according to the Granger test, even if they're completely unrelated.
So cleaning the data first, maybe by differencing it to achieve stationarity, is non-negotiable before running a Granger test.
Absolutely non-negotiable. Otherwise, the results are likely meaningless. Furthermore, the outcome of the test can be highly sensitive to how many lagged values, how many past terms of X and Y you choose to include in the test regressions.
Choosing the right number of lags is critical.
Yes, choosing too few might miss a real causal link, while choosing too many can introduce noise and potentially mask the effect or lead to spurious findings due to overfitting. It requires careful model selection.
So wrapping this all up, what does this really mean for you, the listener, trying to model time series data? It seems clear standard OLS regression is just treacherous ground because of that pervasive autocorrelation.
It really is. Ignoring it leads you down the wrong path.
Statistical integrity absolutely demands we move beyond those standard tools. We need things like the cross-correlation function to even pinpoint the potential lag.
Then sophisticated techniques like error-may error transformations to mathematically achieve those clean white noise residuals when dealing with linear models.
And finally, embracing the flexibility of distributional modeling with tools like gamma SS when our data just doesn't fit the normal mold.
Exactly. Ultimately, modeling multivariate time series is, well, it's often a constant tightrope walk.
Also,
You're always balancing the desire for maximal predictive accuracy, which often pushes you towards adding more complexity, more lags, nonlinear terms, intricate distributional assumptions against maintaining model robustness, interpretability, and avoiding overfitting. Multiple regression is complex enough, applying it to time series adds layers of difficulty.
so even with these powerful techniques,
Even with powerful tools like GAMLS or carefully constructed Aramax models, never, ever skip the final sanity check, the eyeball test.
just plotting the predictions against the actual data.
Yes, ply your model's forecasts against what really happened. If the forecast doesn't look intuitively reasonable, if it wildly misses obvious patterns, then no matter how statistically sophisticated the model claims to be, its practical value might be zero. The statistical soundness might be purely theoretical if the result is practically useless.
That's great practical advice. So here's a final thought for you to maybe explore further as you dive deeper into these topics yourself. If we fully accept that Granger causality is fundamentally based purely on whether one variable improves the prediction of another, and we now have these incredibly flexible, often nonlinear tools like GAMLS that can demonstrably provide superior prediction compared to the simpler linear models traditionally used in the standard Granger F-test.
Right, a nonlinear model might capture predictive power. A linear one misses.
Then how might we need to adapt or extend that traditional F-test framework to rigorously assess predictive causality when the underlying models we're comparing are themselves complex, nonlinear, maybe even distributional like GAMLS? That F-test relies on linear assumptions. What comes next?
That's a very interesting question, pushing the boundaries of how we test for influence in complex systems.
Something to think about.